Afternoon. Good afternoon, everybody. I'm going to speak about some commonalities between COVID-19 and flame blowout. And I am an engineer, nut and bolt engineer, that type. And I work on jet engines and rocket engines. So wherever I see, even if I look into epidemiology, I would see flames and that kind of stuff. I mean, there is a saying that if you wear red glasses, you see the world as red. Blue glasses, you see world blue. Yellow glasses, you see the world yellow. So that's very true in this case. And I had the great fortune to work with a fine physicist, Induja Pauthar, and a fine mathematician, Ankan. Induja is doing postdoc in Ben Gurion University. Ankan is somewhere around here. And he is a fine mathematician. So together we worked on this problem. So, COVID-19 created lots of problems and disruptions in our life. And COVID-19 Delta wave in India was extremely rapid and was growing faster than what anyone expected. In fact, actually, if you remember that people were declaring victory over COVID somewhere at that time. And I also thought that, okay, maybe we can breathe free. And then this thing started. And I know nothing about virus, nothing about epidemiology, nothing about any of these things. But I work on forecasting this phenomena called transitions and combustors, like dangerous situations where the combustor blow up and so on. So that is my bread and butter. So I accidentally saw this graph with Induja, and we were looking at some ways of how the fluctuations are in predicting these transitions like flame blowout and thermoacoustic instability. And Induja told me one day that this is actually log periodic oscillations, and she said that this was really going to blow up to a hyperexponential curve, and it was nowhere near the peak, but we're going to go several fold. And then she said we should work really hard and in a day or two put it in archives because she said it was going to blow over. Then she told me that I'm having a headache, I think I'm dehydrated, let me go and sleep. Tomorrow we'll work 36 hours in a row and finish it. But that was it. Everyone fell sick. Entire group was sick, 4 of them in ICU, and it took a lot of toll and trauma. So there went the idea with archives. So it took a really long time to reboot and come out of all this. But eventually we published, but by then everything is over. But still, I mean, it was fun. I thought we would tell the story, although it took a while to tell the story. So okay. So the wave actually, what I showed was the zoom portion here, but it just went up very rapidly. I think this is not really, okay. Maybe there's a delay. So we were not prepared for such a sudden increase in COVID cases, and we had acute short of oxygen, and you saw these scenes in real life or TV, and I was begging with hospitals for ICU admissions for some of my students and postdocs. And it was really bad, and I was not sure whether I was sick, everybody was sick, and it was really bad. And if we had got some early warning, because by the time they imposed lockdown during Delta wave, it was already at the peak or very close to the peak. And if people had some reliable way of knowing that this was going to come, as Induja has predicted, then we could have saved lots of life. Sorry, this thing is probably low in battery. So the exponential growth of number of infections is thought to be the hallmark of this kind of generally epidemic spread in the early phases. And I'm sorry, this is not working. So then how did such a rapid increase in new infections happen for the Delta wave? So if we could get during the initial phase some kind of precursory signature by looking at the data here, then we could get precursory signals a priori, and then we can predict that something is going to happen, and then we could have some kind of measures. So exponential function, probably the most famous function in mathematics. So this is how we look. Everybody knows this. If you plot it as in a semi-log plot, here the abscissa is linear, but the ordinate is log, and then it looks like a straight line. So exponential growth appears as a straight line in a semi-log plot. Now, if we look at plot things in semi-log, and you see Many of them are in straight line. So for example, this is the UK third wave, Germany fourth wave, first wave of South Africa, first wave of USA. They fit the exponential pattern perfectly well. But in contrast to the exponential growth, we also observed faster than exponential growth during the extreme COVID waves. For example, there's India second wave, which is what we suffered. I was just talking about the trauma during that time. It's really, this one, it's concave upwards, or USA third wave, which was very strong, Japan fifth wave, Italy second wave. So these were concave that way. So these are hyperexponential, or it's also called super exponential by fluid mechanics people. And this is a popular function. Growth of human population is considered hyperexponential. Now we also see slower than exponential. For example, in India, the first wave was, or UK, the first wave, that actually is concave downwards, and this was slower than exponential because there were, you remember in 2020 March, there were acute stringent measures. You couldn't go out of your house and so on. So that actually kept the propagation a bit slower. So we see exponential, slower than exponential and faster than exponential variations. It's not just only exponential. At least that's what the data says. So in the current model, it's generally assumed that 1 over I dA by dt, that's the relative rate of change of number of infections, is constant, or dA by dt is like proportional to I. Now, if we generalize this and write that dA by dt is ki power m, then we can get 3 different solutions if you try to integrate this. One case for m equal to 1, that's the exponential case, that is the classical one which everybody talks about, exponential spread. But if m is greater than 1, you would get a solution of this form, there's a power law, with a finite time singularity where as t approaches tc, this will blow up. And for m is less than 1, you will have a slower than exponential variation. So exponential function is just one specific solution to the growth equation. So the power law with faster than exponential growth leads to unbounded growth and finite time singularity at a critical time tc. Now you may ask, what is the problem with unbounded growth? Exponential function also grows to infinity. But the exponential function grows to infinity at time t equal to infinity. Whereas this function, hyperexponential function, it actually blows up at a finite time. So this is called finite time singularity. So exponential growth of infection has a constant growth rate and also a constant doubling time. In contrast, the doubling time is not a constant for a hyperexponential growth. In fact, if you can see that the doubling time constantly shrinks, and eventually it keeps on shrinking that you just tend to some finite time where the infections will blow up. So in fact, there have been reports in the newspapers saying that doubling time worsens and doubling time keeps changing and decreasing and so on. Now, the faster than exponential growth is really hazardous because it's really rapid and it entails, and we need stricter regulations to minimize the further spread. Now, just want to clarify that I'm only looking at the start of it. After some time, the infection goes so high that the virus will run out of people because the people get immunity, and also measures will be in place. People fall sick, they don't come out of their houses, and there will be lockdowns and so on. But at the sudden rapid rise when people are not expecting it, that is a hyperexponential curve. So we can estimate hyperexponential power law exponent alpha and a critical time t. Critical time t, very close to it, it will blow up. And this alpha is something that indicates the rapidity of the hyperexponential outbreak. So just one number we can quantify this, rather than, for example, typically if you see the articles, you see that people characterize the slope at different times because the slope of if you try to fit an exponential function to a curve which is going faster than exponential, you have to get the coefficient growth rate at at different times, and so it's characterized using piecewise exponential, but instead with just one number you can characterize it for hyperexponential. And for every country we looked at a number of cases, and all the extreme waves are actually hyperexponential. We have the statistics to check on this. And if you see, there are fluctuations around this growth function. And these are not really random fluctuations, and they're genuine fluctuations that should not be disregarded as noise. These fluctuations can be modeled as log periodic oscillations. Log periodic oscillation means it's periodic in logarithm. So the waves will have periods which are accelerating, and eventually they will blow up. So let's consider the function x power alpha. This is the classical power law. But now if you have the power law decorated by a function cos of omega log x, so log x will make it accelerate, and cos of log x, that is a periodic function but with accelerating period. So this is actually log periodic function. And so the cosine function decorates the power law with oscillations that are periodic in the logarithm of x. So log periodic oscillations appear as oscillations with increasing frequency overlaid on a power law. Now if you look at the number of infections, it's very hard to see. But if you differentiate this, you can really see this, these fluctuations. And there's a test for log periodicity. We do a spectrum with spectral power versus log periodic angular frequency. This is called LOM spectrum. And if you see a dominant peak there, then this is a test for log periodicity. And you can see that this test is showing that we have actually log periodic oscillations. So log periodic oscillations precede a finite time singularity. They are precursors to a blowing up of the solution. So log periodic oscillations accompanying a power law can be represented as a power law with a complex exponent. So if you can think of this x power alpha cos omega log x, we can rewrite as real part of x power alpha e power I omega log x, which you can actually just do some manipulation and say it's x power alpha plus I omega. So this is like a complex exponent. So yeah, so we have, when you have scale invariance, you have power law solutions. You get f of x is c x power alpha. But when you have a situation where you have discrete scale invariance, discrete scale invariance means that when x equal to lambda power I, where I is an integer, then your invariance hold, and it doesn't hold for non-integer i's. So when x is changed continuously, you will see like a function which is periodic in log. That's the solution you can derive. And this is what I was saying, that's a precursor to the onset of this finite time singularity. So now the question comes, if I have infecting two people, and each of them are infecting two other people, and if each of them are infecting two other people, then you should get some exponential growth. Why do you get hyperexponential growth? The key thing is that the virus mutates, and even in a single being, the virus mutates. And the growth is, the nature favors things that spread fast, grow fast. So the mutation leads to this accelerated growth. So actually, because of the finite time singularity, every time it doubles, but it just gets compressed and you get blow up. So this hierarchical structure of virus spreading with a converging doubling time is what is resulting in hyperexponential growth. And the people with, the researchers showed that there is mutation of the virus, and that's what is, and it happens even inside in continuous transmission among humans. And there are many works which have shown that the thing, virus mutates as continuously actually. So the hierarchical structure of virus spreading with the converging doubling time results in hyperexponential growth. So we have published these results in Chaos Journal recently, last year. And catastrophes happen in nature. We don't like them, but seem to hit us every now and then. And these happen in a wide variety of systems. It's not just in one system. And although these are apparently very dissimilar systems, there are actually quite a bit of similarities. So I will talk about combustion system, which I was originally studying before I got diverted into this corona system. So we look at a problem called flame blowout. You can do this experiment at home, take a candle, blow it, and the flame will blow out. I am not doing the experiment here because then the fire alarm will come on. So flame blowout is very detrimental to the operation of modern gas turbine engines or even power producing engines. Because for example, this is a very famous aeroplane, SR-71, it's also called Blackbird. It's a Cold War vintage fighter, Mark 3.5. But in an airplane, for example, you did some mission, you did some dropping a bomb or whatever, and then you're trying to come back, and you're trying to come back to your base for safety, or you're trying to really accelerate and get to a place where your friends have air superiority. And in that time, and you're really pushing, you're accelerating. And so that means you're pumping in a lot of air coming in, and the flame can blow out, and this is one such thing. And this is disaster, because you're trying to escape from the enemy, and you lost the flame. And then once you lose the flame, you cannot just press a button and flame it will not come. You have to actually come down to a very low altitude and reignite, and then only you will get thrust. And all this in the middle of combat, this is just disaster. I mean, you are gone if you lose your flame inside the engine. You are pretty much dead. So it's really important to ensure that you don't have flame blowout, and this is done usually by putting a lot of margins actually in the system. So we try to study this. We are trying to study this even before doing the corona. So this is like a experimental setup. We have flow, and there is a settling chamber, and flow comes in, and there's a combustor where you can do flame imaging and so on, and we can study this. I don't know if you care about this, probably not, but this is just the setup. And this is how the setup looks like. Very nice design actually by Vishnu and Dilish, some of the finest designers I have seen. Vishnu went to IIT Hyderabad, Dilish went to Applied Mechanics department. So they made this combustor, and this is how it looks like in operation. So if any of you want to see it, you can come tomorrow at 2:30 to our lab, and we'll give a live demonstration of our combustor in action. And it's very intricate, and we make a lot of measurements of that. So recent studies have shown that prior to blowout, combustors exhibit very complex dynamics. Let me try to play this movie. I have to get the cursor. Yeah. So flame just simply doesn't move. It does a lot of things, like it makes big regions without flame, and then it looks like it is gone, and then wait, it'll come back. It should. Yeah, it's coming back. So this kind of very complicated thing happens, and it's complex actually. So we actually unraveled a striking similarity between the growth of extreme COVID waves and flame blowout in engines. So the number of cases in COVID-19, it was going at hyperexponential decorated by log periodicity. So here the acoustic signature from the flame was having this hyperexponential growth, and also this log periodic oscillations. And we also can calculate the doubling time of this growth, and it's actually reduces on approaching the critical time. And so we can also do this test for log periodicity, and we can see that log periodicity, we can draw the LOM spectrogram, and we can see that the log periodic oscillations precede flame blowout. And blowout, we can study in detail. We can do laser imaging and find that blowout is the extinction of flames by formation of global flame holes. It's a big flame hole. You saw sometimes there was no flame. And the number and frequency of excitation and reignition events increases as the system approaches blowout. And so the small holes are there, they're here and there, and they merge to form big ones, and then they burst to form even bigger ones, and the rate of merging actually increases, or the time between merger events shrink. So during blowout, at this finite time singularity, the collective behavior of the flame holes leads to the formation of large flame hole that ultimately leads to blowout. So each extinction is part of a precursory sequence of an even larger event with more local flame holes during such progression. So this is very fine planar laser imaging, not by us, but some of our collaborators. So you can see this small, this is a little bit far, you can see small flame holes, but this is close to the blowout where you can see these big holes. So using the log periodic model, the time of blowout can be predicted actually many seconds earlier, which is very good, because then we can avert getting into flame blowout, and an aeroplane is not in any trouble. We have also patented this, and the hierarchical dynamics underlying the precursory events were utilized actually to predict the corresponding critical phenomena. And this is published in Physical Review E some time back. So several phenomena such as stock market crashes and earthquakes have been found to be preceded by small-scale precursory events. And you can actually see this finite time singularity and log periodic oscillations, hyperexponential growth, etc. in earthquakes as well as in stock market crashes. These are results from SORNet. And so large earthquakes and stock market crashes occur as a scaling up process of the earlier precursory events. And similar features are observed across engineering and biological systems. So the picture here is a test on a rupture of a rocket combustor, again from Sornet, and you can see this hyperexponential growth of the oscillations and log periodicity there. And the growth of human population is shown to be hyperexponential. So these features are seen across many systems. So they used to predict ruptures. I think Sornet has a patent on it to test for liquid rocket combustion chambers, ruptures in engines, population growth, earthquakes, and epileptic seizures. So the dynamics of complex phenomena exhibit generic features on approaching a critical phenomena, regardless of the governing physical process. In very diverse systems, such as a combustor or a jet engine, or in coronavirus epidemic spread, we see very similar phenomena. And so in summary, extreme COVID-19 waves exhibited hyper-exponential growth and log periodicity close to the critical point. And flame blowout is also preceded by hyper-exponentially growing low amplitude oscillations decorated with log periodicity. And log periodic power law can be used to predict these critical points, and it can be predicted fairly in advance. And in COVID, we predicted, but we fell sick, so we couldn't publicize it at the time. And thank you very much.